Okay, so hi everyone, I'm Jacob Isbell. I'm a PhD student at the Max Planck Institute for Astronomy, and today I will be introducing to you the largest existing subarcsecond catalog of active galactic nuclei in the L and M bands. Next. So I don't really need to motivate what a dusty torus is following the previous excellent talks, but I will emphasize that the L and M bands are interesting because they probe the intermediate AGN scales. This is between the sublimation ring that we see in the K band and the hundreds of parsec scale extended dust structures that we see in the N band. Moreover, if we study this regime, which is the interface, if we study this area, which is the interface of these two regimes, we can hope to understand the physics that drive the polar outflows that we see in Circinus, for example. Additionally, with Matisse and JWST looking at these L and M bands, having a catalog of these fluxes can help plan these observations. So our catalog has 119 local AGN, and this means redshift less than 0.3. We have 5 subtypes, the large majority of which are Seifert-2, as you can see in the histogram here. They all come from the parent sample of Asmus et al. 2014, which was the subarcsecond N-band catalog. And they were largely taken from archival data taken between the years 2000 and 2013, and with VLT Isaac before it was decommissioned. And rather than taking aperture photometry of these sources, we've decided to spatially decompose the fluxes. This means that we have a central unresolved component, which should represent the dusty torus itself, and a second component, which is any of the resolved emission. And so I'll quickly go through our flux fitting because it's pretty standard. So we fit 2 Gaussians simultaneously, where one of them is fixed to the size of the PSF, which comes from fitting an elliptical Gaussian to a PSF calibrator observed very close in time, because the atmosphere varies very quickly. And then we also have a second Gaussian, which only has the requirement that it is larger than the PSF. And this can represent the larger scale structure. So with this example here, NGC 4374, we have, although you can barely see it in the image, we see in the slice that there is clearly a central component with this red line, and the blue line is the extended component. And for the rest of the talk, I'll be mostly talking about this unresolved portion, which should be the dusty torus itself. And also, rather than going into the specifics of flux calibration, I thought I would show 2 ways which we could apply these fluxes. So our catalog has 119 sources, but the all-WISE AGN catalog has over 1 million sources. Unfortunately, though, we can't use the WISE fluxes directly for planning at the VLT, and specifically with the VLTI. And this is because all of the photometries they report have a mean PSF of 6 arcseconds, meaning the extended region I just showed would be completely unresolved and entangled up with the dust torus. So what we can do is take our new L band Isaac fits and compare them to WISE W1 and plot this against the WISE W1 W2 color. And here we see for the Seifert 1s in blue and the Seifert 2 in red, a very clear relation up until WISE W1 W2 color of 0.8. After which there's essentially a constant flux ratio between the L and the W1. This means that we can quite consistently convert from WISE to Isaac and vice versa. Similarly, in the M band, we find a constant relation between M and W2 for colors redder than 0.8. Bluer than this, it's harder to say because we have so few sources, but the relation seems to hold. On a completely different note, we can check the validity of various dusty torus models. So we take Skirtor from Marko Selewski, which is 2-phase, and so there's a diffuse dusty component with clumps superimposed, and Cat3D, Cat3 Wind from Sebastian Hönig et al. And this is collections of spherical dust clouds. And so if we plot them here, which is the L over M flux, a proxy for the color, and the M over N flux, we can see one very important thing, and that none of them produce colors bluer than L over M of 1. So what happens when we put our AGN on top of this? We see 2 things right away. One, that many of the AGN agree with the torus models, but you'll also see immediately that many of the AGN are much bluer than these torus models allow. Why is this? Is it a resolution effect due to host galaxy contamination, or is there a misunderstanding of the physics in this 3 to 5 micron bump? So the first thing we could check is the amount of stellar contamination. 24 of the AGN in our sample have symphony K-band measurements of the central 1 arcsecond. This is slightly larger than our mean PSF of 0.7 arcseconds, but it's comparable. And we can also use the K to L band color from Asif et al. 2010 to, this is for old stellar populations in the bulge, and we can use these two things together to estimate the L band stellar contribution in the bulge. And so I plot here the Isaac measured flux versus the expected stellar contribution. And this red line here is 25% stellar contribution. And we see that the majority of our sources have less than this. But we can also apply this as a correction in the model plot that I showed before. And what we see when we do this is that all of the AGN, all the crossmass AGN, become consistent with Cat3D wind, even this very blue one, which has large error bars. This is a strong indicator that the majority of the blue shift that we see comes from stellar contamination within our PSF rather than a misunderstanding in the model physics. And I'll wrap up here. So this is the largest existing subarcsecond L and M band flux catalog of AGN. We report separate L and M band fluxes for the central engine and for its surroundings. We report extensions and position angles of the LM band dust, which I didn't get into too much in this talk. We also related our fluxes to the Ys W1 and W2, which increased our sample from 119 to effectively over 1 million. And through comparisons to the various Torus models, we find that Cat3D wind best matches the measured LM, MN colors, and that our large offsets can be explained by stellar contamination, even though this isn't completely confirmed and interferometric follow-up is necessary to be certain. And lastly, I'll say that this paper is in review, so please keep an eye on the archive for when it's released. Thank you very much.
Thank you very much. Very nice overview. And I like your very nice sticky take-home messages. I like that. Clarity in a talk. Thank you very much. Do we have any questions? Let us see. We're well on time. No direct questions. So I will ask a question that has been driving me. That's more, not only you to you, Jacob, maybe, but all speakers here. In the mid-infrared, if you don't do interferometry, so it's more for those who don't do directly interferometry, we have very low angular resolution. So we see a soup of things. So is there any, so I've been, this is maybe an ignorant question from somebody outside of the field, but what is your benchmark between an AGN? What do you see normal galaxies? I mean, if I just take them, I always take the Milky Way. So we have a tiny black hole in there. We have lots of molecular dust. We have star formation. We have very strong pH emission, as we know from Spitzer. We have all kinds of junk floating around. How can I separate the junk floating around? Like we have an inner molecular disk that is maybe 100 parsecs. So that is, of course, maybe almost resolvable, but there can be also smaller nuclear rings. So how can I keep this apart from a torus? I'm completely, the use of the word torus really is confusing at this moment. Because it's not the classical torus anymore, but is it there? Is it not? How is it related to just stuff floating around in the center of galaxies? How is it related to AGN? So I would be very thankful for clarifications for the outsiders.
Yeah, I mean, it is very difficult to disentangle all of this. And this is part of what we tried to do here by keeping the unresolved component separate from any of the larger scale structure that we see. And it's very small here, and I don't have it available quickly, but in the Sombrero galaxy, for example, we see essentially a large star forming disk in the L and M band still. Okay. And so this kind of highlights the difficulty that you're pointing out.
Oh, thanks, Jacob. That's nice. So can I basically say a provocative statement? So when you don't do interferometry, but lower angular resolution, so basically imaging, is Torus anything that is unresolved currently? Can I say that just provocatively? The definition of Torus is currently unresolved mid-infrared emission. Leo is
kind of,
I don't know,
yes,
what is it?
No. I think maybe for the closest AGN, you can start to resolve it, but certainly for the majority, it would still be unresolved, yeah.
Because I'm not sure whether the Torus is dead now, or is it not dead? Is it there? Is it not dead? I mean, yeah, there's Sebastian Hoenig's model, so there's a Torus and an outflow. So So I always wonder whether we are just driven by our scientific drive to simplify things, to understand them, or is it just junk in different approximations? I'm very provocative in these things.
Can I say something to this?
Please, yeah.
You want to say something?
Well, to your question, I mean, I wouldn't just define it as unresolved or not. To me, the torus was always AGN heated dust. And we see now that most of the AGN heated dust is not in a toroidal direction. So in that sense, the torus...
I have to disagree. we do see, I mean, I think we are seeing at different wavelengths, we are seeing different things. And I think in the mid-infrared, we're seeing the hottest dust emission. And in the with ALMA, the 850 microns, we are seeing these very extended structures that are, you know, torus-like or this key, and it's just part of the same structure. And then we see it also in cold molecular gas. And actually, if you look at that cartoon you showed with that Sebastian produced, he adds all those components. I think it's just that we're still a bit stuck in the old view of the sort of donuts like torus.
No, that I certainly agree, Amadina. It's just that if you perhaps have an additional requirement that the torus is what blocks the light from the nucleus, then I think it gets more tricky yet.
Yes, and with ALMA, what we are seeing is that the column densities that we are getting, with all the caveats, are quite close and correlate with the column densities you get from X-rays. So obviously, it's related to that obscuring material.
May I say something, Rainer?
Yes.
Hi, Christina here. Yeah, I would like to. So I agree with everyone, I guess. But I think something that has changed, no, also in our view of the torus in the last year, comes from putting together all the observations that we have in different wavelengths, like Almudena has said, no. So, for example, in the mid-infrared, no, it looks like most of the emission comes from this polar dust. But in ALMA, we see that, for example, in NGC 1068, half of the torus mass is in the torus, right? And the other half is affected by the outflow or outflowing. And something that has changed also is that the torus is not only the structure that makes the obscuration, but also the connection between the black hole and the galaxy, you know, and a structure that links the two of them and varies within the periods of AGN lifetime.
Okay. And can you benchmark this to non-active galaxies? So what do you see tori in non-active galaxies, or do you not see any of these structures? That would clarify the things very easily.
Well, I'm thinking, for example, the guys in the LAMA, precisely one of the goals, no, of the LAMA. Leo can answer this much better than me, no. But for example, they have collected ALMA data of non-active galaxies, no, matched to an AGN sample, and the idea is to see if we see similar structures, no, as the one that we see in the AGN. So this is the next step, no, to go to non-active samples matched in mass, morphology, etc.
Unfortunately, we don't have the ALMA data yet. We only have APEX data. And on these scales, indeed, we don't see differences in the molecular content on, let's say, up to an arc-minute scale of AGNs and matched inactive galaxies. So if you match by galaxy mass, by Hubble type, and a couple other things, then they look the same. So, yeah.
But on the smaller scales, Rainer, for example, so for example, in NGC 1068, Santi Garcia Burillo estimated that if the torus keeps on outflowing at its rate, it will last for 1 to 4 mega years. So in principle, we would expect to not see tori in galaxy where the AGN is off.
Okay. Thanks.
Yeah, there is evidence of this outflowing torus, basically. So that explains why you not all galaxies are classified as AGN, because it's sort of transient phenomenon.